Hello friends, I am Dr. Mukesh Dimri and this is our lecture number 3 in modern physics, and in this lecture we will discuss the explanation for negative results of Michelson-Morley experiment, then Lorentz transformations and relativistic velocity addition formula, and also we will discuss the acceleration transformations and the possible explanations for the negative results of Michelson-Morley experiment, where first one was ether drag hypothesis. And according to this theory, the moving earth dragged the ether with it. So there is no relative motion between the ether and earth. So that's why there should be no shift in the fringes. But this theory was contradicted by the stellar aberration. Means when we want to see the star from the earth using some telescope, then due to the motion of the earth, we need to tilt the telescope from time to time to see the star. But if this ether drag hypothesis was correct, then we should not have to tilt the telescope. That's why this theory was also not accepted. Another explanation was given by the Lorentz and Fitzgerald, and they suggested that there is a contraction in the length in the direction of motion of in the ether, and in the direction of motion the length contraction was with a factor of under root 1 minus v square by c square, and this contraction will make the path length equal to the length of the other path, and in that case then t1 becomes equal to t2, and then there should be no fringe shift or not any time difference. But this explanation was have also not any experimental proof, so it was also discarded. And the third explanation was given by Einstein, that the motion through ether is a meaningless concept, and then he gave two postulates in 1905. The first one was the principle of relativity, that all the laws of physics have the same form in all inertial systems, and second one was the constancy of the speed of light. The speed of light is same in the vacuum in every inertial frame, regardless the source or the observer is moving or not. So this was used in Michelson-Morley experiment, and they have used the Galilean transformation equation, and they have used C plus B and C minus B. That's why they were expecting some fringe shift, but according to this postulate that the speed of light should be only c, so that's why they could not observe any shift in the fringes. Now we will discuss the Lorentz transformations, because Galilean transformation equations failed to explain the electromagnetic equations in different frame of reference, and according to Galilean velocity transformation, u prime was u minus b, and if in the case of light, c prime was taken as c minus b. So it violates the special theory of relativity or the second postulate, because c is fixed, and so different transformation equations are required to satisfy the postulates of relativity, and it was established by Lorentz a set of transformation equations which have the relativistic term, and these were valid for all kind of systems. Now we will do the derivation of Lorentz equations. So Lorentz modified the Galilean transformation equation, and Lorentz assumed that there should be some extra term k or gamma in relationship between x and x prime, means coordinates of rest frame and moving frame. So x prime equal to k x minus bt. In Galilean transformation equation it was x prime was x minus bt, but there is some extra factor k, it was assumed by Lorentz, and k is a factor which depends on the velocity v of the moving frame s prime. Similarly, for the S prime, the equation will be x will be k x prime plus bt prime. So this is equation number 2, and k is same for both the frame of reference, only sign of b is different. And if there is no difference in y and z coordinates, the motion is only in x direction. So y prime will be y, z prime will be z, and we have this relation x dash equal to x k x minus bt. And if we put this value x prime x k x minus bt in equation number 2, then we will get a relation in t prime, and then we will see that t prime and t, these are not same. And if we put the values here, x was k x prime plus bt prime, so in the here with we can replace x prime with k x minus bt. And if we simplify a little bit, and this is k square x minus k square bt plus k into b into t prime. And here, from here we can find t prime equal to kt plus 1 minus k square by kb into x. So this is equation number 5. Here we can find out t prime, and equation number 1 will give us x prime. So our job is to find out this constant k, which depends on the velocity of the frame. So t prime equal to kt plus 1 minus k square by k into v into x. This is equation number 5. And according to second postulates of relativity, the speed of light c is constant for both the frame of reference, either it is in s frame or s prime frame. So the distance covered in s frame will be velocity of light into t. C into t will give us the distance x in s prime, and in s prime frame it will be c into t prime, because speed of light is here will also c, not the c prime, but it will be c into t prime, and it gives us the distance x dash or x prime. And this if we put the values of x prime and t prime from equation number 1 and equation number 5 we have seen in last slides into this equation number 7, so x prime will be c into t prime, and then we get this equation x prime was k x minus bt, and here in right hand side c, and with t prime can be replaced by kt plus 1 minus k square k divided by kv into c into x. So this was the if we put these values in equation number 7, and if we solve this equation for x, because we want to get this x in terms of t, and we will get x is equal to ckt plus bkt divided by k minus 1 minus k square by kv c. And if we take c into t as common, then we will here we will have k plus b by c, because here c was not there, so c is taken out, b by c k divided by k minus this denominator will be same. So ct into something, and we can write it a little bit, we can simplify it, ct 1 plus b by c, k, one of the k is cancelled out if we take the k common in numerator and denominator also. So k will be cancelled out, and it will be 1 minus k square by k square b into c, and we can write it 1 upon k square minus 1 c by b. So this is the relation equation number 9 is relation x equal to c into t into something. But we have the equation 6 was x was c into t. If we see the in the last slide that in s frame the distance x equal to uh, c into t, the velocity into time. And equation number 6 and 9, these equations are comparable. These two equations are comparable only when this term in the this bracket, big bracket, is 1, then only these equations are same. So x equal to ct into something, x equal to ct, so this whole term should be 1, then we will have x equal to ct. So then to compare 6 and 9, then we will have this term equal to 1, and this whole term is compared with 1 plus b by c divided by 1 minus 1 by k square minus 1 c by b equal to 1, and after cross multiplying and little bit rearranging the terms, and finally we will have a relation, we will find k in terms of b and c. So k square equal to 1 upon 1 minus b square by c square, or k equal to under root 1 upon 1 minus b square by c square, or under root 1 minus b square by c square. So this was the aim of this exercise, to find out this k, which was in x prime and t prime. So k, or in some books this is written as gamma. So now we put this value of k for x prime and in equation 1, and for t prime in equation 5, and then we have the expressions given as x prime equal to x minus bt. It was k into x minus bt, so k is 1 upon under root 1 minus b square by c square. So this is Lorentz equation. Y prime is equal to y, because there is no motion along y and z axis, and t prime is t minus b x by c square. K, in place of k we will write 1 upon under root 1 minus b square by c square. So this is, we can see that t prime and t are not equal, as it was equal in the Galilean transformation equation. So these equations have now the relativistic term also, which is 1 upon under root 1 minus b square by c square. And this k in many books it is written as gamma, so it is the 1 upon under root 1 minus b square by c square. And for remembering, we can just write x prime equal to gamma x minus bt, y prime is y, z prime is z, t prime equal to t minus bx by c square into gamma. So these are the Lorentz transformation equations. And for small velocities, if b is much less than c, then this b square by c square term is negligible, and then these equations they reduce to Galilean transformation equation. In that case, x prime will be x minus bt, and this whole term b square by c square is negligible, so it will be 1. So it is Galilean equations. Y prime, z prime is the same. T prime equal to t, this b by c square will be very small term, and b square by c square is very small term, so these can be neglected. So t prime equal to t. So for small velocities, or if v is much less than c, then in that case these Lorentz transformation equations they becomes the Galilean transformation equation. So these are the general transformation equations can be applied to any kind of velocities. And inverse Lorentz transformation is just for the observer. If it is in s prime frame, then x will look like x prime plus bt. Only we will have to replace by minus b. So x prime plus bt by under root 1 minus b square by c square. Y will be y prime, z will be z prime, and t will be t prime plus bx by c square under root 1 minus b square by c square. So for the inverse transformation, if x prime, y prime, z prime and t prime are given, then we can find out x, y, z and t in S prime using the inverse Lorentz transformations. So there is one question that prove that x square plus y square plus z square equal to c square t square is invariant under Lorentz transformation. So invariant means if we put the transformation equation for primed coordinate x prime, y prime, z prime and t prime values here, then it should be in similar form. Then we can say it is invariant under Lorentz transformation. So we already know that in place of x we can write x prime plus bt divided by under root 1 minus b square by c square, y equal to y prime, z equal to z prime and t equal to t prime plus b x by c square divided by under root 1 minus b square by c square. And if we put these all values in this given equation, then we will find, we will get after many terms will be cancelled out, we will get only x prime square plus y prime square plus z prime square left hand side, and right hand side we will get c square t prime square. So this is in the same form as it was in S prime, in S prime. In S prime it was, this equation was like this, and in S prime frame this equation has only primed coordinates and it is in the same form. That's why we can say that this equation is invariant under Lorentz transformation. Now we will see the velocity transformation, and it is for the relativistic velocity addition formula and for the all kind of motions. So using the Lorentz transformation equations, we can find out the velocity transformation. So we know x prime, y prime, z prime and t prime equations, and the velocity component in frame S, or in if the observer O is in frame S, then dx by dt will be ux component, dy by dt will give us uy component, and dz by dt will give us uz component in frame S. And in frame S prime, we will have the primed coordinates. So velocity will be ux prime dx prime by dt prime, ui prime will be dy prime by dt prime, and uz prime will be dz prime by dt prime. So now we have to find out the velocity components in S prime frame and S prime. How these are correlated, ux prime and ux, ui prime and ui, and uz prime and uz, how these are related using the Lorentz transformations. So if we take the small changes in x prime, y prime, z prime and t prime, then we can denote the small change by this symbol, triangle symbol. It is known as delta, or in some books you will find it is small, it is written as dx. So small change in x prime will be dx or delta x. So delta x prime equal to delta x minus b delta t, and this 1 root 1 minus b square by c square, this is constant term because b is constant, c is constant. And delta y prime will be delta y, delta z prime will be delta z, and delta t prime will be delta t minus delta x, b by c square is constant, under root 1 minus b square by c square is also constant. So these are the small changes in x, y, z and t coordinates. And if we divide this delta x prime equation with delta t prime, this first equation to fourth equation, then we will get delta x prime by delta t prime as delta x minus b delta t divided by this factor, and denominator delta t minus delta x b by c square by divided by this factor. So this 1 minus b square by c square under root, this will be cancelled out. We will have delta x minus b delta t minus, divided by delta t minus delta x into b by c square. And delta x prime by delta t prime, we can write it as ux prime because it is dx prime by dt prime, that is ux prime or ux dash. This is the velocity in S prime frame. And on right hand side, if we take delta t as common, so delta x by delta t will give us ux minus b, and delta t also from the denominator we take out. So 1 minus delta x by delta t b by c square, and delta x by delta t can be written as ux. So it will be ux prime equal to ux minus b, this is ux minus b divided by 1 minus ux by c, b by c square into ux. So this is a relation in ux prime and ux. So this is the velocity transformation in using the Lorentz transformation equation, or it is known as the relativistic velocity transformation for the x component. So ux prime equal to ux minus b divided by 1 minus b by c square into ux. So in Galilean transformation equation, it was only ux minus b. So this is the extra term here, and these equations are valid for all kind of motion, even either the velocities are relativistic, or if for the low velocities it will be, this term will be negligible, again it will be Galilean velocity transformation. So this is for the ux prime. Similarly, we can find out for the y prime and z prime using these two relations. If we divide this equation 2 by delta t, delta y prime by delta t prime will give us ui prime, and delta z prime by delta t prime will give us uz prime. And now we can just find it, delta y prime by delta t prime, delta y under root 1 minus b square by c square divided by delta t minus delta x b by c square. So this if we divide this equation by this equation, then little bit we have to simplify it. Again we will take delta t common from the denominator, and this is delta t 1 minus delta x by delta t b by c square, and delta y by delta t can be written as uy, and delta y prime by delta t prime can be written as uy prime. So uy prime equal to uy under root 1 minus b square by c square, and denominator will be same as ux prime, that is 1 minus ux into b by c square. So this is just, we have to rearrange the term, and for this term we will write prime term, and this non-primed will be uy. So again we have a relation now uy prime and uy. And similarly we can find out delta z prime by delta t prime. So delta z divided by delta t minus delta x b by c square divided by 1 minus b square by c square, which will go in numerator. And again we have to just rearrange the terms. This left hand side is uz prime, and here delta t, if you take from denominator, so delta z by delta t will be uz under root 1 minus b square by c square, and denominator 1 minus ux b by c square. So this is uz prime and uz relation in uz prime and uz for the z component velocity components. So this was how we can transform the velocities of one frame of reference to another frame of reference for the relativistic case. And for the acceleration transformation, so this is just summary that ux prime is ux minus b, denominator 1 minus ux b by c square. Ui prime and uz prime are little bit different than the ux prime. We can see the numerators ui under root 1 minus b square by c square, and denominator is same 1 minus b by c square into ux. uz prime uz 1 minus under root 1 minus b square by c square 1 minus b by c square into ux. So denominator is same in all components of velocity, but only difference in the numerators. Similarly, inverse velocity transformation will be when we know the ux prime, uy prime, and uz prime, and we have to find ux, uy, uz. Then we will have to use the inverse transformation equation. That is, ux will be ux prime plus b. It will the only sign will be changed. 1 plus ux prime b by c square. Uy will be uy prime under root 1 minus b square by c square, but this denominator b sign will be changed. And similarly for the uz. So these are the velocity transformations or the relativistic velocity transformation components. For the acceleration, we need to differentiate this velocity transformation equation, which was first we will get for the ux, and for the ux prime was ux minus b divided by 1 minus ux by b ux by c square into v, and we have to differentiate it with respect to t prime. So left hand side will be dux prime by dt prime will be d of dt prime of this whole thing. So we can write it as first function ux minus b, and second function we can take 1 minus ux b by c square to the power minus 1 if we take it in numerator. Then it is product of two function, and we have to differentiate with respect to time. So left hand side will be dux prime by dt prime. This will be ax prime, and here the product of two function will be the first function ux minus b into differentiation of second. So difference is 1 minus this ux b by c square to the power minus 1. So it will be minus 1, this whole power minus 1 minus 1, it will be minus 2, and then differentiation of this term, the differentiation of ux into b by c square, and v by c square is constant, so it will be constant. So we will have dux by dt prime, and dux by dt prime can be written as dux by dt into dt by dt prime, and plus the second term. Now we will have this 1 minus ux b by c square to the power minus 1 second function into differentiation of first, and differentiation of first will give us delta ux by delta t prime only, because v is constant. So delta ux by delta t prime, we can write it by chain rule delta ux by delta t and dt by dt prime. So this is, now we have to just rearrange the term. So this was the product of two function, and we were differentiating with respect to t prime, but here we can take with the ux, we will take dux by dt into dt by dt prime with the chain rule, so that we can write it ax. So for simplification, we will take the this outside of this bracket dux by dt into dt by dt prime. This is in both the term, these terms are common. So we can take these out, and just we can write ux minus b, b by into, if we multiply it inside this, and then we will have first term will be ux minus b, b by c square, and if this 1 minus ux b by c square power minus 2 will go in denominator with plus 2 power, plus 1 divided by 1 minus ux b by c square if we take this in denominator, and this dux by dt is ax, left hand side is ax prime, and dt by dt prime is here, remaining term is here, and inside this we can take the uh, LCM of this 1 minus ux b by c square whole square, and this will give us ux minus b into b by c square, and plus 1, it will give us something 1 minus uxb by c square, and this bx by c square will be cancelled out. We will have only term 1 minus b square by c square on numerator, and denominator 1 minus uxb by c square whole square. And finally we have this these terms, ax prime equal to ax 1 minus b square by c square to the power 3 by 2, and in denominator 2 power is here and 1 power is here, 1 minus uxb by c square, so it will give us 1 minus uxb by c square to the power 3, and if in terms of gamma, 1 upon gamma means 1 upon under root 1 minus b square by c square, so it will be 1 upon gamma cube, 1 upon gamma cube this term. So ax prime equal to ax by gamma cube, and then this whole term 1 minus b by c square into ux to power 3. So this is the acceleration components in relation in the ax prime coordinate and ax coordinate. Similarly, we can, if we differentiate the y prime coordinate of the velocity component with t prime, we will get the y component. This was x component, and similarly we can find the components of acceleration in y direction, and for that we will have to use the uy prime, that is uy prime equal to uy under root 1 minus b square by c square divided by 1 minus ux by c square. And if we differentiate again with respect to t prime, we have to follow the same procedure we have done in last slide. Here this 1 minus b square by c square is constant, we can take it out, and we have the function uy into differentiation of d by dt prime of uy first function into second function is 1 minus this denominator term 1 minus uxb by c square to the power minus 1, and just we have to again rearrange the terms, and finally we will get the answer ay prime in terms of ay and ax. Here ax is also term is also there, and we will get, if we put the gamma as under root 1, this should be under root 1 minus b square by c square. So ay prime equal to gamma square 1 minus this ux b by c square cube and uy b by c square plus ay divided by gamma square 1 minus ux b by c square whole square. So this is the term for y coordinate or y component of the acceleration ay prime, and relation in ay prime with ay, and there is also ax term is also there. In az prime term also az term is there, and also ax term is also there. So this is how we transform the acceleration components in primed coordinate to non-primed coordinate, and this will depend on the gamma also, because gamma means under root 1 minus b square by c square factor. So this is how we have started from the Lorentz transformation equation, and then we have established the velocity transformation and acceleration transformation. So these equations are valid for all kind of velocities, and for low velocities these are reduced to Gaussian transformation equation. So these are the components of acceleration in y and z axis. So thanks for watching this video, and if you have any queries, suggestions, then please write in the comment box. And previous video we have discussed the Michelson Morley experiment, and in next video we will discuss the length contraction and time dilation. So thank you very much.